But y'all, Darley Berber Jr. back for some more quantum physics. So I'm going to continue with where we left off at. So this is a continuation from the previous stream. And we'll jump right into it. So what I'm thinking about doing is, last time we did the non-degenerate state for the two-dimensional well. Before you move to fine structure, let's repeat one of the degenerate states and see what that looks like. So I'm thinking maybe this one here, the psi 1,3 and psi 3,1. So we'll look at some degenerate perturbation theory. So the formula degenerate perturbation theory is going to be this. This is basically the quadratic formula, and Wij is this. Right? So what we'll do is go right ahead, see what this will look like for this scenario. So psi I equals psi j, and if we want the further degenerate state in x equals 3 and y equals 1 and y equals 1 and x equals 3. So yi equals ya equals psi 3, 1, and psi j equals psi b equals psi 1, 3. So WAB is psi 3, 1 prime psi 1, 3, which we write this in integral form. And I'll bring up my notes, make sure I don't mix it up. Yep. So it looks like this is going to be And again, the psi j here, uh, j, I guess this should be n m ij equals psi n m psi m n. I see psi n psi m. All right, there we go. I think that is proper notation. So we have integral, double integral, 0 to a of psi 1 girdle 2 over a sine 3 pi x over a square root of 2 over a sine pi y over a v naught square root of 2 over a sine pi x over a sine 3 pi y over a dx dy. So to simplify this and make it into 2 and set the boundaries over the area of the potential, we have 4 of these, like a left off one. So we have 2 over a squared. So that's 4 v naught over a squared. And we have potential x from 0 to a over 2. Now this is sine 3 pi x over a sine pi x over a dx. And integral now is power over 4 to 3 pi over 4 is a over 4. So we have a over 4, 3a over 4 sine pi y over a sine 3 pi y over a and dy. So this is the degenerate matrix element. Matrix element AB for the degenerate state of 3 and 1 in the x and y dimensions of a two-dimensional potential well. So I do notice that WA and WB will be the same. So it's just, it'll be, the x will have a 1 first and the 3 second. So we can see that this also equals WBA. So we have 4 V naught over a squared. And now we can actually square this. But it is 2 odd functions, so that should be even. And is over half. It should give us a value. Oh. How would I do this? I might put this in mathematical. Let's see what the manual way to do this would be. I have to say maybe I can split them into two, but I don't think that'll work. Could do integration by parts. You have to do that twice. Let's see how that works out. And actually, I'll just pull up Mathematica, see what it says. That'll say save some time. But is an interesting thing to look at later. I'll probably go ahead and do if I had to do this manually, probably will go ahead and do integration by parts and see what happens. But I don't want to take the time to do that at the moment. So let's see what Mathematica says. This is going to be integral. I'll take the constant out. Actually, leave the constant in. For b over a squared sine 3 pi x over a and sine 1 pi x over a. And we're going to integrate x from a over 2 to 3a over, so it's 0 to a over 2. Right, so this came up as 0. So I would have thought the sine is odd. I'd have thought these two equations would have came up as, but I always get mixed up with the even odd thing. So 3 and 2 gives an answer, but 3 and 1 does not. Right? It's equals 0, which means that the other side must equal 0 as well. Now looking at this, the 1 wave function will look like that, and the 3 should look like that. But that'll explain why they balance out to 0, because of the wave functions, how they interact. But maybe I should look this up really fast. Sure, showing. I'll look up, oh, this, and again, it's Darrell Lee Berry Jr. back with some uh, perturbation theory. Show why this is blinking. So it looks like there's still a product of some identity, which I forgot about. So again, we're looking at this degenerate perturbation theory. Uh, this is the equation for the energy of the uh, first degenerate state. This is the matrix element of the uh, matrix that we can use to determine the energies with the eigenvalues and the eigenvectors. And this is the equation for the integral of the WAB matrix element. And now we're looking at how that equals 0. Now, and I forgot that this is not, the bounds are not offset. So apparently these bounds here this is the product of some identity. We have two signs. It's sine A, sine B equals 1/2 of the sum cosine A minus B minus cosine A plus B. Right, so let's see what this looks like. I could have typed this into Mathematica wrong. So let's try this identity out, see what happens. So I'll take just this first half. equals right. So this equals 0 a over 2. And you can do each of these separately as already in the cosine form. To pi over 2 or pi minus 1/2 sine of 0 is 0. That is 0. That does in fact equal 0. The sine of pi is 0 and sine of 2 pi is 0. All right. Check one more thing. Maybe I made a mistake in here somewhere. Let me see. Looks like this is what it ends up being due to orthogonality. And so that means that WAA, WAB equals WAA, BA equals 0. Now we have WAA, which equals psi 1, 1, psi 3, 1, 3, 1. And by the way, diagonality of sine, this will likely come up again. Full, if we have the full domain, that is 0 to a, sine a, sine b, or maybe I should put the full thing, n pi x over a, m pi x over a. This is going to equal 0 due to orthogonality. Half domain, which is 0 to a over 2, equals 0 sometimes, depending on the bounds. And arbitrary domain, why don't we go ahead and test this out with the different bounds. So we can actually start here. Everything up to here is the same, except we have y, and we have a over 4, 3a over 4. So we have 1/2. Actually, all of this will be the same. Taken notice. So we have sine 2 pi, and this is going to be, the a is going to disappear, 3 over 4 minus sine 4 pi, 3 over 4 minus 1/2. So this is just a over 4 2 pi over 4 minus sine pi. So this equals 1/2. So we have sine of 3 over 2, 3 pi over 2. So that's something 0.08 minus, I could just put this on the outside, a over 4 pi. Does all of those have that? Oh, 2 of them do, 2 of them don't. So this is 4. And we have sine power over 2, which is 1. Minus a over 8 pi. And we have sine 3 pi. That's going to be calculated in degrees. That should be 0. 0, 5, 0. So these will be 0. Those will not. Equals negative over 4 pi 0, 2. It's going to be times 4 VO over A. Forgot the other side is going to be 0 anyway, so it's all 0. All right. So it looks like there's no matrix element for WB WAB. So if I were to do WAA, and copy this, and both of the x's will be 3. Both of the y's will be 1. And I'm going to put this straight in mathematically and see what we get. So this is WAA. Both of the x's 3, both of the y's 1. So I'll pull the x's out. And again, the x's are 0 to a over 2. And the y's are a over 4 to 3 over 4. See if this keeps the same. Looks like it would for the a over 2 ones, because those are odd, so it should still be orthogonal. It's interesting. We have both to the x, so they're the same. Actually, they won't be. We have 3 pi x squared. That came up to v over a. And then we have need the coefficient for this one. And now we have 1 and 1, and it goes from a over 4 to 3 over 4. Okay, this is a big ugly number. One pi y, 1 pi y over a, pi over 4, 3 over 4. Yeah, so that equals out to be 2a minus pi a minus 3 pi a minus 2a sine of, if I could did not calculate the last one, 3 pi over 2, or 8 pi. So the a's will of course cancel. All right. Simplify this a bit. Thought mathematical would. So that's negative 1 over 8. So that equals negative v naught over 8. Let's check this. Seems like a valid number. I might have multiplied an extra 2 in there somewhere. I believe it's 3 pi over v over 4. But the process is correct. So that is WAA, and WBB would be the same thing, except now the Y's would be the double threes. So the bounds would be different on the double threes. So it would be 3 pi and 3 pi with a bounds of 0 to A over 2. And then the whole thing disappeared. Another ugly number. So Mathematica, either I'm typing this in incorrectly or it's giving some crazy numbers. Process is correct. So now that we have that, we can use this equation to get the energy. But since all we have is the WAA and WBB, it'll end up just being that anyway. Uh, so look at this equation. WAB and WB is 0. This becomes 1/2 WAA plus WBB plus or minus square root of WAA minus WBB squared. That becomes 1/2 WAA plus WBB plus minus WAA minus WBB. So for plus, it'll be 1/2 of 2 WAA, which equals WAA. And for minus, it'll be 1/2 so WAA will subtract WAA, so it'll be WBB plus WBB equals WBB. That means that since the diagonals are 0, we already have our uh, first order corrections to the energy, the plus and minus. And then all that's left to do is to get the degenerate states. So since the eigenfunctions themselves are the states, the psi 1, 2 and psi 2, 1, or in this case, psi 3, 1 and psi 1, 3 are the first excited degenerate states. Write the formula just in case we get something that's not. So if we did have to figure it out, it'll be the second order correction equal. So one thing. first order wave function. Scroll too far. Equals, so it's going to be a sum. Uh, it so happens that with this scenario, uh, WM, which is really our WA, is going to be psi 3, 1, and this is going to be psi 1, 3. And so we're going to have x3 and x1 over the perturbation. So x3 will be over the half, so that should be 0 like it was before. So therefore the same states are how it works because the diagonals are 0. Well, that's why we don't use this equation, because it's just going to 0 out. But if the diagonals were not 0, then we would get another value. Then we would have to solve it. And we didn't even get to find structure. But that was more important. So I may come back another time to do that. I'll go ahead and take a break, and probably be back next week, and we'll continue on. So have a good evening.